Okay, this is the last lecture on Chapter 7. We're going to discuss very briefly determinants. We'll start out with a simple discussion on second and third order determinants and then generalize it to nth order determinants. You might have noticed by now that in this textbook, as a general rule, the discussion starts with a more simplified case and then extrapolates to the more complex case. So basically, a determinant of second order is defined as followed. It has the same elements as a matrix, but notice that we have vertical bars instead of square brackets. That denotes the difference between a determinant and a matrix. A determinant also has a specific value. The determinant has to be square in order to get a solution. In this case, the value of the determinant of this matrix A is the difference of the cross product of the terms, as shown here. For a 2x2 matrix, we can actually get a solution to equations in two unknowns by evaluating in the following way. So D is the determinant of the coefficient matrix that was shown on the previous slide. If we have the set of equations equal to a set of B's, we basically take the B vector and we substitute it in the column corresponding to the x1 coefficients. So we substitute B1 and B2 here. We take the value of that determinant over the value of D, that will get us x1. To get x2, we would substitute the B vector into the position of the matrix where the coefficients would multiply x2. Divide that by the value of the determinant D, and we'll then get the solution for x2. A couple of issues. One is if D is equal to 0, and that becomes a problem and the system becomes unstable, so Cramer's rule can't always be applied to solution of linear systems in the case where you have a determinant that has a value of 0. A determinant of third order is shown here. Notice once again it is square. Basically, the determinant of third order, we can choose any row or column. What's going to be illustrated here is the choice of the first column, and so we're going to divide this into determinant and subdeterminants known as a minor. So basically we take this column, we're going to take A11, A21, and A31 in sequence. The way this works is the first row, first column has a positive sign associated with its coefficient. Second row, first column will have a negative sign. Third row, first column will have a positive sign. So when we take the first A11 term, we basically are going to eliminate the first column and the first row. What's left is called the minor, and that will become the determinant that multiplies A11. We then move on to the second term. We strike out its column and its row. What's left? A12, A13, A32, A33, negative sign here, and then do the same with the third term in that first column, getting its minor as well. If we were to write that out, this is the expression that we would get for that 3x3 matrix. Sorry, 3x3 determinant. So Cramer's rule can be similarly applied, illustrated here, where the only difference is when we're solving for x1, we would take the coefficients associated with x1, and in the determinant d1, we substitute the b vector, and then x1 will be the value of d1 over the value of d, the determinant of the coefficient matrix, and so on. So Cramer's rule is relatively straightforward for 2x2 and 3x3 systems of equations. Now, if we want to generalize that, we can have a determinant of matrix order n. And notice here the textbook author has written an m here, but it is critical that you understand that m is equal to n. This has to be a square in order for the determinant d, in order for the matrix A to have a determinant. So this would have to be square, m would have to be equal to n. Also notice it is possible to have n equals 1, and in that case the determinant is just the value of the A11 coefficient, so it has to be square. I think this is an example of maybe a little laziness on the author's part. He probably copied a previous matrix and didn't change the m to n. So this is sort of a generalization of if you're going to pick your minors and cofactors, remember it could be any row or column. In the previous example, we picked the first column, so our coefficients had a plus, minus, plus. Had we picked the second column, our coefficients would have had a minus, plus, minus. And this can be extrapolated to an n by n, that basically your plus and minus signs will form a checkerboard pattern. And so that's an easy way to keep it straight rather than memorizing a complicated formula. Easier just to visualize the checkerboard, in my opinion. So here's an example of a third order determinant of expansion by the first row, and here's example by the third column. So third column, 0, minus 4, plus 2. First row, 1, minus 3, and 0. When solving determinants, it's always convenient, if you can, to pick a row or a column that has a 0 in it, which makes one factor go to 0. Modern calculators, as well as almost all software, including MATLAB, will do determinant and matrix expressions. So here's Cramer's theorem stated generally for an nth order system. So as long as that has a non-zero coefficient determinant, we can have a theorem that the system has precisely one solution. And that solution can be given by the following formulas. And we have previously described how to get D1. We basically would take the B vector and substitute it for the coefficients multiplying x1. Continue that in sequence all the way through xn, and you'll get the specific solution. So if the system's homogeneous and D is not equal to 0, it will have only the trivial solution. If D is equal to 0, then the homogeneous system will also have a non-trivial solution. Okay, so that basically concludes the use of Cramer's rule and determinants and a few definitions. Most of you have seen this before, but hopefully you've learned how to do this on your calculator, which makes things relatively easy. And so this concludes our lectures on the textbook material from Chapter 7.